Hello everyone. In this video we're going to go over a basic introduction into Pennylane, which is a Python library for differentiable programming of quantum computers. So the idea is to go over some simple examples so that you get familiarized with the syntax used to create circuits and simulate them within Pennylane. A few prerequisites for this video. Well, first of all, you need to have Pennylane and Jupyter notebooks installed. I'll add a link in the description below to help you with this. And also, it's important to have some basic familiarity with quantum computing. So nothing too sophisticated, just understanding quantum states and their representation in both bracket notation and state vector notation. Also, how quantum states evolve over unitaries. So making sure that you know if you apply a certain state psi through, let's say, a gate, you know what the evolution of that state is, and also how to deal with composite states, so states with more than one qubit. Okay, so let's start with a very simple example. So let's start with a 1 qubit circuit where we initialize that qubit in state 0, and let's say we apply an X gate followed by a Hadamard gate. And we're interested in finding out what the state psi at the output is. So after applying this X gate, we're gonna end up with state 1. And then applying a Hadamard gate to state 1 gives us the state minus, which is an equal superposition of 1 over root 2, state 0 minus state 1. And in state vector notation, this is equal to 1 over root 2, 1 minus 1, which is the same as, or approximately the same as 0.707 and minus 0.707. So now let's go into Pennylane and create this circuit and evolve the state 0 through it. So the first thing we're going to do is we're going to import Pennylane as QML, and here QML stands for Quantum Machine Learning, because as we discussed in the introduction of this video, Pennylane is a library for differentiable programming of quantum computers, which is a big part of quantum machine learning. So this alias just has been the convention adopted by Pennylane from the beginning. Next, what we're going to do is just define a Python function, just a regular function. We're going to call it qfun. And inside this function is where we're going to apply our gates. So the first gate in our circuit was an X gate. So we do qml.polyx. And it's very important to write poly here because there is also an X method within Pennylane that is for a different paradigm of quantum computing known as continuous variable quantum computing. So if we use X here, it won't throw an error, but it won't apply the X gate that we're hoping to use. So we always have to apply polyx here. Then to this method, we're going to pass wires equals 0. And wires here denotes our qubits. So when I say wires equals 0, that means apply this polyx to qubit 0. And the reason the term wires is used here is because, again, Pennylane can be used for different types of quantum computing paradigms. So wires is a more generic term compared to qubits. And then we're going to apply our Hadamard gate also to qubit 0. So wires equals 0. Now here, we don't necessarily need to explicitly write wires. We can just ignore that if we pass this as the first parameter. And then what this function is going to return is qml.state, because what we want to simulate is the evolution of state 0 through the circuit, and then we want to look at the state at the output. Now to simulate this in Pennylane, what we need to do next is define a device. So the way things work in Pennylane is we have quantum functions, so what we just created, this qfun, and then we have a device, which could be a simulator or an actual quantum processing unit. And in Pennylane, we need to wrap this two around what is known as a Q node. So we're going to define our function, which we did already, then specify our device, and then we'll pass this to our Q node to execute the simulation. So now we're going to define our device by using QML device. And here we're going to pass a name, which the standard qubit simulator in Pennylane is known as the default qubit. And then we need to specify the number of qubits we want to simulate. So in this circuit, we only have one, so we do wires equal 1. And then after defining our device, we can now create our Q node. So we do Qn for Q node, QML Q node, and then we pass our quantum function and our device. So one of the things we can do now that we have a Q node is we can look at our circuit or draw our circuit. For that, we use QML.draw. And here, what we're going to pass is this quantum node, which is a function. And then this QML.draw is going to return a function. So we need to execute it. So we need to add this parentheses here at the end. And this is going to return a drawing of our circuit, but using text. So we can just print that out. And then we can see here that we have our state 0, then we apply the X gate, then we apply a Harlmer gate, and what we want at the output is to see what the state is. Pennylane also has a nicer way to display circuits by using the draw MPL function. So we can do QML.draw MPL, and then again we pass our quantum node, and this returns a function, so we need to execute that function. And this returns a matplotlib. So MPL stands for matplotlib. It returns a figure and its axis. So we can assign this to a figure and its axis. And then by executing this in a Jupyter notebook, it will automatically display the quantum circuit. So here we go. This is a nicer way to display the circuit. Now, this might be a little bit confusing because here it's showing a measurement block, but in reality, we're really not measuring anything yet. We just want to simulate what the state, the quantum state at the output is. All right, and now if we want to see what the state at the output is, all we need to do is just execute our Q node. So I'm gonna save it in a variable. I'm gonna call it SV for state vector. And then I'm just gonna execute our quantum node and then print that state vector. And so here we go. This just gives us the state of the output, which is 0.7 and minus 0.7. So to recap, we created a quantum function which has the gates we want to apply to our circuit and specify what we want to see at the output of that circuit. Then we define a device and we wrap the two around a Q node to execute that simulation. Now in Pennylane, the recommended way of executing these 3 steps is by actually taking our device and defining it. And then instead of just defining the function and then passing that to the Q node, they recommend using what is known as a decorator. So in Python, you can use decorators to enhance the functionality of certain Python functions. And that's exactly what we do here. So this quantum function we're defining here, we can decorate it with QML QNode, and we specify the device that QNode is going to take. And what this does is it takes the function right below that decorator and upgrades it from just a regular function to a QNode using this device. So here, the name that QNode is going to take is the same as the one you give to this function. So now we can call this just directly QN, and this does exactly the same that we described, but just by putting this decorator, we don't need to specify this extra line here that we had, QML.QNode, and then passing the function and the device. This decorator on top does that for us. So here you can see that I still have my QNode. So if I print that, I get the same result we had before. So what are other things we can learn from this circuit? So we found the output quantum state, but we could also ask, okay, what if I now add a measurement block here, And I'm interested in finding out what are the probabilities of measuring either a 0, which is associated with projecting the state into state 0, or measuring a 1, which is equivalent to projecting the state into state 1. So we could ask, what are the ideal probabilities? We know that if we have an arbitrary state, let's call it psi equal alpha 0 plus beta 1, from the Born rule, the probability of measuring state 0 is the norm of alpha squared, and the probability of measuring state 1 is the norm of beta squared. So in this example, our alpha is 1 over root 2, and our beta is minus 1 over root 2, which means that the probability of measuring 0 is the norm squared of 1 over root 2, which is a half. And the probability of measuring 1, well, it's the same, but with a minus here. But since we're taking the norm square, it's also a half, right? So how do we find this in Pennylane? Well, it's very simple. Now that we have defined this Q node, well, we can here, instead of returning QML state, we can now return the probabilities for that Q node. And if I execute this and now print this, instead of getting the state vector, we're going to get probabilities of measuring 0 and the probability of measuring 1. So another thing we can learn about this circuit is, for example, finding the total unitary from input to output. And how will we do this? Well, it's as simple as just saying, okay, the total unitary is the multiplication of the matrices of the X gate and the Hadamard gate, right? So now recall that because here the matrices operate on states that are on the right side, like this psi, then the order of multiplication has to be first the Hadamard gate and then the X gate, so that in the circuit in this direction, we first apply the X gate, then the Hadamard gate, but when we're doing the math here with matrices, we first apply the X gate and then the evolved state, then to the evolved state, we apply this Hadamard gate. So then to find out what this matrix looks like, well, we simply take the Hadamard gate, which is 1 over root 2, 1, 1, 1 minus 1, and multiply it with the X gate, which is 0, 1, 1, 0. And the total unitary for that is going to be 1 over root 2, 1 minus 1, 1, 1. So in Pennylane, what we can do is simply use QML matrix, and here we're going to pass our Q node, so Qn. And as you've probably seen so far, most of Pennylane's methods take as inputs functions and return functions. So every time you do this, you need to execute whatever this method is returning. So in this case, we're going to get the total matrix for our circuit, and here we have it. So as we expected, 1 over root 2 minus 1 over root 2, 1 over root 2, and 1 over root 2. So one thing to note here is that this matrix method ignores what the Q node function is returning. So here I could change this for state, and obviously we will get the same type of matrix. So this is important to note, because in some other quantum computing frameworks, if you have some sort of measurement here that would collapse the state, you would not get the unitary matrix. You could get, for example, a non-unitary matrix, including the measurement. But that's not the case in Pennylane. So to avoid this type of confusion, what I typically like to do is actually separate the unitary part of the Q node from whatever we are asking about our circuit. So the way we can typically do this is, well, we can then create a function, let's call it circuit, where we have all our circuit components. So we're going to have our gates here. And then this is not going to return anything. This function, when we execute it, is just going to apply these gates. And then we can just call that function within our Q node. So this will basically call the gates and then return the state, for example, right? So let's, for example, call this qn sv for state vector. And then here, if we print qn sv, then we're going to get our quantum state. And then what we can do is, now that we have defined this circuit with our gates, we can now call it to do different things. So now here I can call this, for example, qn probs, and then here I ask this to return the probabilities, and it's calling the exact same circuit, but instead of getting the state, it's getting the probabilities. So then if I print, let's execute this, and if I print qn probs, then this gives me the probabilities. And then if I want to get the unitary matrix, well, then I could do it on this Q nodes, right, as we just demonstrated. But instead, to avoid confusion, we can just get the unitary of this regular function itself. So we can do QML matrix of our circuit. And again, we pass a function, and this returns a function, so we need to execute it. And here we have it. We have our unitary matrix for that particular circuit. So what else can we learn about the circuit? So we've done the state vector. We found the ideal probabilities. But one thing we can do with a simulator is emulate as if we were running this on a quantum computer. So basically execute the circuit one shot at a time and get a result, and get the samples out of it. So to do that, we would do a new Q node, right? And here, instead of asking for the probabilities, what we can do is sample. Now here we have to specify on which qubit we want to take the sample. So if we have a multi-qubit circuit, we could get samples for individual qubits or the whole register by specifying the wires. We'll do that later on. But here we only have one qubit, so we're just going to do wires equals 0. Now, here's the problem. If we execute this, how many times is the circuit going to run? We have not specified that anywhere, right? So the device that we were using, let's go back up and find the device we specified, was this default qubit, but we never said how many times to execute the circuit in this device. Why? Well, because we were just getting the state vector, which is, just the unitary evolution of our state, and the ideal probability. So we weren't really performing any samples. So if we want to run the circuit several times, we need to tell that to the device. So let's just copy this and paste it down here, and maybe let's call it device 2. And here what we're going to do is add another parameter called shots. We're going to say, okay, run this circuit 100 times, or execute 100 shots of this circuit. And obviously here we need to now, for a Q node, tell it that it needs to use this device instead of the one we had defined before. So let's take a look and see what we get. So now if we do, let's say samples equal, let's rename this so we don't confuse it with the one with the ideal probabilities. Let's rename it QN samples, right? And let's say samples equals QN samples. And then let's just print that. And here we have it. So ideally, we should be getting half of the time 0 and half of the time 1. And we can check that by using, for example, from NumPy. So let's import NumPy as NP. And let's use this function, np count non-zero. And let's find out from the samples how many of them are equal to 0. So exactly 50. And let's check how many of them are equal to 1. It should be equal to 50 as well, right? Because we run the circuit 100 times. So we were lucky. We got exactly half and half, but this is not always going to be the case. So for example, if I rerun this, I get a different set of samples, and now we get 56 and 44. And it will change every time we execute the circuit, right? And if I run it 1,000 times, let's just not print that right now, but let's count how many we get. So 495 and 505, which is close to 50%. Now, here's an interesting thing I want to point out. So in the previous device that we used, we hadn't specified the number of shots. And when we asked for our QNode to return the probabilities, it just gave us the exact probability of measuring 0 or 1. But what would happen if we execute quantum node for probabilities with a certain number of shots? Well, if we go down here and now define this again, but instead of using device def, we use def2, which is the one that has, in this case, 1,000 shots. When we call for the probabilities here of this Q node, what we will get is actually the frequentist probability of that sample distribution. So basically it counts in a given execution how many times it got 0, how many times it got 1, and then calculates that probability by taking the number of zeros divided by the total number of shots and the number of ones by the total number of shots. So we don't get the ideal probabilities once you specify number of shots. And if we rerun it, we just get different values every time. So I think this is worth pointing out because it can be confusing if we don't specify that. And if we, for example, ask for the state, so let's say Qn here, let's call it SV, and here return state, what we'll see is that if we execute this, what we get is the exact state. Well, we do get a warning, as I pointed out, saying that the requested state or density matrix is being found with a finite number of shots, and the return state is analytic. So basically it's unaffected by sampling or by measuring the circuit. So it's the ideal unitary evolution of the state through our unitary circuit. So it gives you a warning about that, as I had pointed out before. Another thing that is relatively easy to do with Pennylane is to not just perform measurements in this traditional way of executing the circuit and getting the results in the computational basis and associating, a bit 0 when the state gets projected into the state 0 and measuring a bit 1 whenever the state collapses to state 1. But we can also specify a particular observable that we want to measure. So what do we mean by this? So when we have our circuit here, we said, okay, this measurement block, what it's supposed to do is every time our superposition is measured, then when we get state 0 in the measurement, then give us this bit 0. Whenever we get a 1, then gives us state 1. But we can specify, for example, to measure an observable like the poly Z observable, where the result of the measurements are the eigenvalues of the Pauli Z matrix. So in that particular case, every time our state is projected into state 0, what we measure is the eigenvalue 1, and whenever that state is projected into state 1, we're measuring the eigenvalue -1. And this is for Pauli Z observable. So in Pennylane, what we can do here is now, let's go back here to where we were measuring the samples, for example. So here we have it. We were doing 1,000 shots here. Let's change it back to 100. And here what we can do is inside this sample block, we tell Pennylane that we want to sample the QML poly Z observable, and then we need to specify on which qubit. And if we execute that, and now let's reprint this, now we will see that we get -1 and 1 accordingly. And we can do this for many different observables. For example, we could do it for the poly X, and then when we measure that, we always get -1. Why is that? Well, if we take a look at what are the eigenstates of the poly X observable, so let's erase this here. Well, the poly X observable, when we have state plus, it returns a 1. When we have state minus, it returns a -1. Well, what is our state at the output? Well, it's state minus. So we would always measure the state -1 when we're measuring the poly X observable. And that's why we get 100% of the time -1 measurement. Another very helpful function in Pennylane is that it allows us to compute the expectation values of some observable. So just a reminder, an expectation value in this context is just a weighted average of our samples. So let's say we run our circuit. Let's do a simple example. Let's say we run our circuit 7 times, and our samples. Let's say we measured it in the poly Z basis, and we got -1, 1, 1, -1, -1, 1, and -1. So the expectation value is simply the weighted average of this. So we count the number of -1s. So that's 1, 2, 3, 4. So we do -1 times 4 plus 1 times the number of 1s. So that's 1, 2, and 3, right? Divided by the total number of samples. That's 7. So here we have -4 plus 3. So that's -1/7 will be the expectation value of this limited number of samples. Now, if we break this down, we can see that this expression here, it's -1 times the frequency's probability of measuring -1. So this is the probability of measuring -1. And 1 times this right here is the frequency's probability of measuring 1. So the ideal expectation value of measuring the Z observable, or this poly Z basis, when we have our state at the output, which is our state minus, is basically -1 times the probability of measuring -1 plus 1 times the probability of measuring 1. So, for our state minus, we know that the probability of measuring -1 is 1/2. The probability of measuring 1 is 1/2. So this ideally should give us 0. So let's go into Pennylane and let's take these two cases of computing the expectation value for a limited number of shots and the ideal expectation value for some observable. So in Pennylane, what we can do now is, so let's first define our QNode. So let's do qml.qnode, and let's use device def, which is the one with no number of shots. So that's going to compute for us the ideal expectation value. And let's define, let's say, qn expectation value of z. And let's just call our circuit, which has our gates, and then return qml xval of qml poly z. And then we need to specify the qubit in which we want to measure. We only have one qubit, so it'll be y is equal to 0. And then when we execute this, let's do print our expectation value function, then we get 0 as we had calculated. Now let's switch this device for the one that has 100 shots, right? So if we go back up here, when we defined device 2, we still have 100 shots. So let's change that here. And then we now are not going to get the ideal expectation value, but we're going to get some number that, and in our handwritten example, we got -1/7, but here we're getting different numbers, but they should be relatively close to 0. And we can do the same thing for any other observable. We could do it for the poly X observable, which, as we saw, always gives us, let's go back up here, and when we measure samples on the poly X observable, we always got -1. So obviously the expectation value of measuring this observable when we have the minus state at the output should be -1, because we always measure -1, right? So we can do that down here. Let's say for the one with the limited number of shots, then we can just print that. And we're going to see we always get -1. Lastly, let's take a look at how we would specify an example with more than 1 qubit. So as we did before, we can define a circuit. Let's call it circuit 2. Now we're going to define the gates. Let's say we have a Hadamard gate in qubit 0, and then we're going to apply a CNOT gate, and we're going to apply it from qubit 0 to qubit 1. So for that, we need to pass an array where we say 0 and 1, because this is a 2-qubit gate. So that defines our circuit. Then we need to define a device now. We do that using the QML device again with our default qubit simulator. But now we need to specify that we want to use 2 wires, and we can also specify a number of shots if we want to. Let's not do that right now. With this device, let's call it actually device 3, we can now define our Q node. So QML, Q node, we're going to use device 3, and then we define our QN, Q node. Let's actually call it Q node 2 for 2 qubits, for example. And we're just going to call our circuit. And let's return, for example, just the state at the output. So let's do return QML state. And here I just misspelled qubit, so let's just fix that. Now let's execute that. So now let's take a look at our circuit. We'll do QML draw, pass our QN2, and execute it, right? And we're gonna print this. And here we have it. We have Hadamard gate on qubit 0, and then a CX gate between qubit 0 and qubit 1. And we can take a look at the state of the output by just printing our Q node. And here we have it. We have 1/√2 in position 0 and 1/√2 in this position 3, which is an equal superposition of state 0, 0 and state 1, 1. And we can do the exact same things we've defined before. So for example, we can define a Q node that calculates some expectation values for this circuit. And one thing we can show here is that we can say, okay, calculate the expectation value of the poly Z on, let's say, qubit 0, and the expectation value of the poly X on qubit 1, for example. And if we execute this, we get our result here of 0. Or we can do, the ZZ expectation value, which should be ideally 1. The last thing I want to discuss in this video is the concept of parametric quantum circuits, which are a key component in the differentiable programming of quantum computers. So let's say that we have the same circuit, our Hadamard gate and a CX gate, but let's actually redefine it down here. Let's do circuit 3, And let's replace our Halomar gate with, let's say, an Rx gate, so a gate that rotates our quantum state about the x-axis by some angle. So here we specify on which qubit we want to apply it, but we also need to give it an angle of how much we want to rotate that state by. So we can say, okay, we're gonna rotate this by some angle theta, and then we're gonna have to pass that parameter to our quantum circuit here. So we're gonna define here theta as well. And then we can now define our Q node, where we're gonna use that same device 3, which uses 2 qubits. And let's just call this, let's say QN3 state vector. And that's gonna call circuit 3. But here we have to pass that angle of theta as well, and our Q node has to take that as an input parameter. Let's say we're going to just return the state here. Okay, and now if we want to execute this Q node, well, we would have to call our QN3 as V, but then we need to pass some number, right, some angle. So let's say we want to evaluate this circuit at an angle of pi over 2, for example. So from numpy, which we already imported, we call pi. And let's just print that state vector. And here we can see that we get the right output. But the advantage here is that now we can pass different values to this as we are continuously updating some other parameter on a bigger algorithm. So this makes it very flexible and allows us to create programmable circuits. Now, one last thing I want to highlight here is that if we want to draw this circuit, so let's say we do QML draw, and we pass this QN3 Q node, well, the problem is that this function needs some parameter as an input, so we can't just execute this without passing something to it. So we always need to pass some sort of number even to draw the circuit. So if we pass here this pi over 2, and again we pass to this draw function the QN3 Q node function, but not evaluated, and then we evaluate what this draw function returns by passing that parameter, and then if we print that, we can correctly get the circuit that we want. It shows the Rx gate with the angle we're passing and the Cx gate as well. So that's it for now. Planning to upload more videos on Pennylane. This was just the very basics, but I hope you liked it and hope you keep watching.